Think of memory in C like a warehouse, but not every warehouse works the same. Here we have two different types of memory, the stack and then also the heap. The stack works exactly as you would expect. It is data organized in a stack the same way you can organize boxes in a stack. But of course, when you want to add to that stack, we have to add from the top. And when we want to remove from the stack, we always have to remove from the top as well. The last one in is the first one out. Now, this is all great, but what does it mean in terms of code? Now, if you've written any code, you've used the stack even if you didn't know it. Just by me defining an integer x here, I've added a variable onto my stack. I can also just assign it a value, and well, I've just created a variable x which has the value 10 onto my stack. And I can do whatever I want with it within my stack frame, and we will talk about what that means in a short moment. Now we can print this value, of course, and nothing crazy will happen. We know that it will just print 10. Great. Now this stack that we've just created, this stack frame is for this function main, and once we are past the scope, this curly bracket, the stack itself that's when it ends. That's when the data starts to leave the stack, when it empties itself. Now we can't really observe that here because the main function is active throughout the entire program. But if we were to create a second function called array, and this will return a pointer to an integer, and within this function we will define a array which has the values 1, 2, and 3, and we will return array. Now returning an array, of course, we don't return the whole array, we return the memory address of this array. And what we could do here is set a new variable called integer y. Well, it's not an integer, it's a pointer to an integer, because that's also what an array really is. And we can call this function. Now just looking at this, we've called this function. So here we initialize this array, and this array is initialized within this stack frame. Now we return this address onto y. So that means here we should be able to take the address y and more specifically access the, well, let's say the 0th index of y. Now this is great, right? This should print 1. Now we will have a little problem here, and the compiler tries to warn us before we run that the function returns address of a local variable. But let's say we want to ignore this and we want to print. We get a segmentation fault. Now why is that? Well, in this function here we've defined a stack frame as well within the scope, and this array is defined right on that stack. Now that's all great if we wanted to access stuff here, if we wanted to print this inside of this stack, that would have been fine. But here we return the address to this array, but after this return statement we are completely done with this function call. So the stack frame itself closes, and what happens is all the data leaves the stack. So here this y is not aware that the stack is closed. It just contains an address. It could be an address to anything, right? And here we try to access the 0th index stored at y. Now this address of course doesn't exist anymore. So we're trying to access data that we don't even know what it is. This memory could be used by a different program. The compiler could have used it for anything else. And we're not really allowed to access it. And that's why we get a segmentation fault. We get the core dumped. And that's basically how the stack works. Anything defined within here, if we try this instead now, and we try to print a decimal integer again, and well, it's not called y here, it's called array, and the 0th index again, and we could just remove this completely. And if we try to compile, well, we're gonna get an error completely because we can't return this at all, and we should probably switch this to void. Now we also need to call this, of course. So when we compile, everything's great, and we get the 0th index because we've made that print function within the stack frame of this function. Now, the stack does have a lot of constraints. We didn't even talk about its capacity. The stack isn't infinite and can actually run out of space, so it's best used for smaller sized data. Now, all of these constraints might seem like limitations, but they actually make the stack predictable and as a result, very quick. The heap, on the other hand, is like a warehouse with very little organization. You can throw a box anywhere you want, but it'll always be there and will never disappear until you tell it to disappear. Now, you aren't really placing boxes randomly. You ask the compiler to allocate you space. Then, the compiler will allocate that space on the heap and return you a pointer to that data. Now, the space will always be occupied by your data, and the compiler will keep track of this. But as you can imagine, slowly the heap might get full, and you can run out of space. Because of this, if you want to use this power of allocating space yourself, then you also have the responsibility of telling the compiler when you are done with that data and to free that space for future data to occupy. Using the heap is a little bit more tricky and it is slower than the stack, but it allows us to control the lifetime of our data. There is no stack that will collapse. As long as the data has not been freed and you have the pointer to it, then you can use it wherever and whenever you want. So now back in our code, in order to have access to our heap, we need to include the standard lib.h library, and this gives us two very important functions, our free and our malloc. Now, you might have seen it earlier in the explanation, but basically here, instead of creating this array like this, what we can actually do now is have it as a pointer, and this can be equal to malloc, because this function itself, remember, this is calling the compiler to set space on the heap and it will return an address. Now, what it takes here is actually the number of bytes. You can't just put 3, because 3 what? It doesn't know. What if you want 3 floats, for example, right? So what you need to do is figure out how big is an integer. So we can use the size of function and pass the integer like this, and this will return the number of bytes that an integer is, and now we can just multiply it by how many ever integers we need, and in this case we just did 3. Now what we can actually do is just initialize it like this. We can just do this. You can also just set it up as a for loop, but I will just keep it like this just keep it simple. Now we also need to return array. Here in our main function, let's have our pointer y, and we will equal it to array, to the function array. Now, of course, we need to also return this. Now, we've returned an address, and just to show you that now you still can access these indexes, we can go ahead and actually print the 0th index right here. Remember before, when we initialize this on the stack, once we get to this point, the stack itself closes and this becomes a segmentation fault. But if we were to compile and then run, we're able to access that value. Now, there are a few things to take into consideration. If we use a tool such as valgrind, this is just a debug tool, we can see what it says here. 2 allocs, 1 free. Now, what does this mean? This means that we've allocated onto the heap more times than we have freed. And now, that is a problem that we discussed earlier. We don't want our heap to get empty. If we want to be able to use malloc, we also have to be able to use free. So after we are done, we need to free whatever data that we've allocated on the heap, and we do this by passing the address that the compiler gives us. And if we go ahead and run it, it still runs perfectly fine. If we run valgrind, we get 2 allocs and 2 frees. Now, say that we free this before we actually access it. We get this random number. Now, this is the equivalent of a segmentation fault, because this is memory that we're not supposed to be accessing anymore. This address has been freed. It's no longer on the heap. The compiler has used that data for something else. It might have needed it for anything else. And you trying to access that address is trying to access old memory that we shouldn't have access to anymore. Now, another thing to keep in mind is something like this array. And let's say we're not even printing it. Let's say we're just printing just a message. Let's say that this function has some other side effect where, oh yeah, I think this might be better. Let's say we actually print %d. Let's say we print the 0th index within this function. Now, this might look completely fine to you, which it sort of is. It prints here 1. But if we run Valgrind, of course, we have a problem. We have 2 Alex and 1 free. Now, the problem, of course, is that we've used malloc here, and we never freed it. But if we come here to free, well, we don't have an address to free anymore, right? So that's something that you do need to keep in mind. That address that you receive, you would have to do this in this case. You would need to keep track of that address in order for you to actually free it. It's either we keep track of it here, or we can also free within the same scope. But if you free within the same scope, it loses its purpose really, because you could have just initialized on the frame.